Hi, my name is Matt Turl. Welcome to the Computational Mathematics tutorial. In the previous chapter, you saw how to solve linear algebra problems in MATLAB. In this chapter, you will learn how to solve ordinary differential equations, or ODEs, numerically in MATLAB. Throughout this chapter, we will be investigating the problem of a space probe landing on a distant planet, and looking at how we can obtain the solution to this problem. We'll begin by investigating how Euler's method can be implemented in MATLAB to obtain a numerical solution to a first-order equation. We'll compare this method of solving ODEs to using MATLAB ODE solvers. Next, we'll see how to solve higher-order systems by reducing them to first-order systems. Finally, we'll explore how to use MATLAB ODE solvers to perform event handling and solve stiff systems. Imagine the scenario of a spacecraft landing on a distant planet. A simplified model of this probe in descent considers just two forces acting on the probe. The force of gravity accelerates the spacecraft toward the planet, and drag force, due to air resistance, slows it down. Here is the free body representation of the landing spacecraft. The spacecraft is modeled as a mass falling in free space, with the force of gravity accelerating the mass downward. The displacement is measured vertically upward from the planet's surface. This implies that the velocity, y dot, will be negative as it moves toward the surface of the planet. The drag force is proportional to the square of the velocity, in accordance with standard aerodynamic models. By summing the forces, we obtain the second-order differential equation in terms of the displacement y. We can then reduce this equation into a first-order equation by expressing it in terms of velocity rather than displacement. The result is a first-order, nonlinear, separable, ordinary differential equation for v. We can take a qualitative approach to understand the general behavior of this solution. In this case, by setting the derivative of velocity to 0, we can see that there is an equilibrium solution, v star, at plus or minus the square root of g over d. We can then sketch the possible solutions. If the magnitude of v is less than the magnitude of v star, the derivative of velocity, or acceleration, comes out to be negative. Hence, the solution will decrease toward v star. Conversely, if the magnitude of v is less than the magnitude of v star, the acceleration comes out positive, and the solution will increase toward v star. Therefore, regardless of the initial velocity, the object will approach v star, which is the terminal velocity. To obtain a more precise solution, the traditional analytic approach can be used to solve this first-order ordinary differential equation. For this equation, we can separate the variables and integrate on both sides to obtain the solution. The exact solution obtained can then be plotted and analyzed. However, finding an analytic solution is possible only for a small subset of ODEs. And even if a solution is available, it may be too complicated for the behavior of the system to be obvious. For example, it is not clear just from inspection that this solution will asymptotically approach terminal velocity. To solve ODEs where it is not possible to obtain an analytic solution, we can use a numerical approach to obtain approximate values. This method enables us to obtain a numeric solution and can be applied to all ODEs, regardless of their complexity. The accuracy of the approximate numerical solution depends on many factors, including the system equation type, solver choice, and error tolerance chosen. In this chapter, we'll explore how to calculate numerical solutions of ODEs as we continue to add complexity to our model. In this section, you will learn how to obtain numerical solutions for first-order ODEs, which forms the basis for solving any ODE. Numerical methods for solving ODEs generally work by finding the derivative of the ODE based on an initial value. This value of the derivative can then be used to approximate the value of the solution at a future time step. This procedure is then repeated to step through the solution in time. We'll briefly review different methods for obtaining numerical solutions. We'll then see how to use MATLAB ODE solvers and compare solutions obtained from different methods. The simplest numerical method for solving ODEs is the Ford-Euler approximation. To apply this method, we start with a given initial value of the solution at time 0. In our example, we start with the initial velocity of the probe. The derivative at this initial point can be evaluated using the ODE. At the same time, the derivative can be approximated using a secant line approximation. This approximation can then be manipulated to obtain an equation for successive velocities. The resultant equation uses the current velocity to approximate the velocity at the next time step, t plus h. Here we see that the slope is used to linearly increment the solution by one time step. This leads to the next successive point at time t0 plus h and velocity v1. Again, we evaluate the derivative of the velocity from the ODE and obtain v2 at the next time step at t1 plus h. We can repeat this procedure until the final desired time is reached. You might have noticed that the approximation error could be compounded over time. To obtain a more accurate approximation, in general you can use a smaller time step. However, smaller steps means more steps need to be taken, which means more calculations, leading to longer computation time. So there's a trade-off between the solution accuracy and the computation time required. Let's see how we can implement Euler's method in MATLAB. Here is the script cm Euler versus analytic.m that implements Euler's method for the falling probe. We start by setting the initial conditions for the ODE. Here we have approximated the drag coefficient and gravity for a typical sized probe falling on Mars. Next we set the time step of 1 second, the stop time, and create the time vector. We pre-allocate the memory for the velocity vector by creating a vector of all zeros. Euler's method is then repeated within the for loop. In each iteration, the derivative is calculated using the ODE, and the approximated velocity at the next time step is determined. Finally, we calculate the analytic solution, and we plot both curves to compare the results. Euler's method shows some error initially, but converges with the analytic solution eventually. In this case, the accuracy can easily be improved by taking small time steps. If we look at the script a little closer, we can see that this implementation of Euler's method can be applied to any arbitrary first-order ODE by changing the initial conditions and ODE. Let's see how we can capture this implementation as a more generalized function that can be used to solve other ODEs. Here is the function Euler.m, where Euler's method has been written to solve a general first-order ODE. It takes as inputs a handle to the function that defines the ODE, the rate equations, the start and end time, the initial conditions, and the step size. It returns the time vector and solution values. In general, rate equations are usually specified as functions of x with an independent variable t. Therefore, this implementation of the Euler method in Euler.m passes both t and x to the function f when calling it. Now we can apply this function to our problem. But how do we specify the rate equations? To solve an ODE using a numerical solver, we first need to have the rate equation as a function in MATLAB. Here we've already created a function, fallingBody1.m, that takes two inputs and returns the first derivative of v. Note that t does not show up in the rate equations, but fallingBody1.m needs to have two inputs to be consistent with how it will be called from the solver Euler.m. Although in this example the rate equation only needs v to calculate the derivative, other ODEs might need t as an input to calculate the rate equation. Since we do not use t, we can replace it with tilde. Now that we have the function for the rate equation, here's the syntax for calling Euler.m. The @ symbol creates a function handle, which is a reference to a function. You can find more information about function handles in the documentation by entering doc function_handle in the MATLAB command window. The other inputs, start and end time, initial conditions, and time step, are numeric and can be entered as values or variables. Let's see how we can call Euler.m to solve fallingBody1. FallingBody1 has to be passed to Euler as a function handle. Inside Euler.m, the first input argument, f, is assigned this function handle that points to the rate equation. F can then be used like any function, and wherever f is used, the rate equation function will be called. Here we are going to use a smaller step size of 0.1 to get a solution with 2001 points. We can then plot v against t together with the analytic solution to visualize the results. We can see clearly that the numerical solution is more accurate now that we are using a smaller step size. We've seen how to solve ODEs numerically using Euler's method. However, in practice, the trade-off between step size and accuracy makes this method too inefficient for real problems in general. Additional methods achieve a higher computational efficiency by evaluating the derivative more than once per time step. This allows the solver the option of taking a larger time step when accuracy is not compromised. One approach is the Runge-Kutta methods, which are single-step methods. Single step means that the solver uses a single initial point, tk yk, to step forward to the next time step, tk plus 1 yk plus 1. Within each step, the solver calculates multiple intermediate steps before making the final step to tk plus 1 yk plus 1. The process is repeated for each step, similar to the Euler method. Another approach is to use previously calculated steps to determine the solution to the next time step. This is how linear multi-step methods work. MATLAB has several ODE solution methods available. They all start with ODE, followed by numbers and letters that identify the solver type. Let's see how we can use these solvers. All MATLAB ODE solvers have the same calling syntax. You might find this familiar since it is very similar to calling Euler.m, which you saw earlier. The inputs for ODE 2.3 are a function handle to the function that defines the rate equations, a time vector with the initial and final times, and the initial value of the dependent variable. Notice that there is no need to provide a step size. This is because the MATLAB ODE solvers are variable step methods. They adjust the step size automatically. You can find out about the syntax of calling the ODE solvers by searching for ODE star in the documentation. We'll also see how the solver works under the hood later in this section. By visualizing the solution, we can see that a larger step size is taken when the slope of the curve is relatively consistent. In this case, ODE 2.3 uses only 26 steps, which is almost a tenth of the number of steps
that Euler.m used, for even better accuracy. used, for even better accuracy. What you're observing is the combination of two advantages of ODE 2.3 over Euler's method, which we will explore further. ODE 2.3 solver has two advantages over Euler's method. ODE 2.3 is a higher order method, and ODE 2.3 automatically controls the step size while maintaining accuracy. For the falling body 1 example, we are able to obtain an analytic solution. So we can calculate and plot the relative error at each point for both numerical solutions. See the script CM Euler versus ODE 2.3.m. We can see that the relative error for both methods is on the same order of magnitude. The ODE 2.3 solver achieves a lower relative error, but more importantly, uses only 26 steps instead of 2000. Euler.m simply returns the value calculated with the given step size. Without an exact solution or performing some other calculations, we have no idea what the error is in that approximation. The automatic step size selection provides multiple benefits. First, it removes the need to guess what an appropriate step size is for your problem. Second, the step size is determined so that the error is kept below a chosen tolerance, given you have already learned how to solve first-order ODEs numerically. These methods can be applied directly to solve systems of first-order ODEs. In this section, you will learn how to reduce higher-order ODEs and higher-order systems to a first-order system. This will enable you to numerically solve these higher-order systems using the techniques you have already seen. So far, we have considered a very simple model, for which an analytic solution exists. However, a more realistic model would take into account the change in atmospheric density as the spacecraft falls to a planet's surface. This could have a large effect on the aerodynamic drag. Gravity also becomes stronger closer to the surface. Therefore, the atmospheric density and gravity are no longer constant, but vary as a function of the height y instead. This results in a second-order ODE. To use the solvers that we have seen in the previous section, we can convert this second-order ODE into a system of first-order ODEs. Let's start with the second-order ODE for the system. Here the height y appears on the right-hand side. We can substitute velocity v instead of y dot as we did previously. However, this gives a single ODE for v dot, but it is still a function of v and y, both of which vary with time. Since we know that v is y dot, by definition, we can include this, resulting in a system of two linked ODEs, one for y dot and one for v dot. This is a two-dimensional system of first-order ODEs. The two dependent variables are y and v. Note that the rate equations are determined entirely by these two dependent variables and the independent variable t, although t does not appear in this example. Now that we have defined our first-order system, we can create a function in MATLAB to represent this system. To do so, we have to represent the system in vector form. We first define a vector z with y and v as its components. z1 is y and z2 is v. By taking the first derivative of this vector, we obtain the ODE z dot as a function of the vector z. Notice that this is equivalent to the system that we set up previously. We can then substitute z1 and z2 for y and v respectively. Now that we have our first-order system of rate equations, we can create a function to implement them. Here's the function falling body 2 that allows us to evaluate this system of rate equations. As seen previously, the first input argument is ignored.
The second input argument is the dependent variable z. Using the fact that y is z1, we can calculate the density as a function of z1 using this particular model of the atmosphere of Venus. We calculate the gravitational acceleration similarly. The output is a vector of the derivatives that is the same size as z. Therefore, we first initialize a vector of zeros of this size to guarantee that the output has the same size as the input. Then we implement the rate equations. Once we have the rate equations defined in a function, we can solve them numerically using a MATLAB ODE solver exactly as we did before. In this case, we will use the ODE 4.5 solver, which is generally a good solver to use by default. The inputs are a function handle to the rate equations, a vector of the initial and final times, and the initial conditions. Note that the initial conditions, z0, is now a column vector containing the initial condition for each of the rate equations. ODE 4.5 returns two variables, the times and the values. However, because the dependent variable is a vector, the output z is a matrix containing two columns. Each column contains a component of z, and each row corresponds to a time in t. So to plot the height, we plot the first column of z against t. Similarly, plotting the second column of z against t plots the velocity. As you can see from the results, the descent starts with the spacecraft accelerating toward the planet. However, after 17 seconds, the spacecraft has fallen about 100 kilometers, and atmospheric density has increased sufficiently to start slowing down the spacecraft significantly. What you have just seen is an example of converting a second-order equation into a two-dimensional first-order system. This approach is a common and useful technique that enables you to solve any first or second-order equation using one of the MATLAB ODE solvers. Here is a recap of the steps involved. Starting with a second-order ODE, we first redefine the time-dependent variable y as z1. Next, we take the first derivative of y, or equivalently z1, and define that as the next auxiliary variable, z2. We can then define the vector z and substitute z1 and z2 into the original second-order ODE to obtain a function in terms of t, z1, and z2. This results in a two-dimensional first-order system in z1 and z2. Having converted a second-order ODE to a first-order system, we can extrapolate this technique to convert higher-order ODEs to a first-order system. The process for converting a second-order equation to a two-dimensional first-order system is actually applicable to any order of ODE. An nth-order equation can be converted to an n-dimensional first-order system. To convert higher-order ODEs to a first-order system, we follow these steps. We start by redefining y as z1. Next, we take additional derivatives and obtain z2 equals y prime, and so on, up to the n-1 derivative of y. We can then define the vector z and redefine the ODE in terms of t and z. The resulting system has n-1 equations that come directly from the definition of the variables, and the last equation comes from the original ODE. All ODEs, regardless of order, can be converted to first-order systems using this technique. To solve higher-order ODEs by converting them to first-order systems, let's see how we can apply this to the spacecraft landing problem. If the spacecraft enters the atmosphere at an angle instead of vertically, the air resistance will act against the trajectory of motion, while gravity only acts vertically. In this case, we have to set up a system of equations to represent this two-dimensional system. Here's the free body diagram of the spacecraft landing on Venus, entering the atmosphere at an angle. The angle theta identifies the direction of the spacecraft's trajectory. By resolving the forces, we obtain a system of two second-order ODEs that represent this 2D system. In the x direction, we have only the drag force resolved by cosine theta. In the y direction, we have both the drag force and the acceleration due to gravity. Given the two equations of motion, we can consolidate the drag coefficient into a function d of y. Finally, we can substitute x dot and y dot for v and theta to arrive at the two second-order equations in terms of the dependent variables. Given these two second-order equations, we can set up a vector of auxiliary variables. In this case, we will need 2 for each second-order variable. By taking the first derivative of this vector, we can convert the two equations into a four-dimensional first-order system. Notice that the left-hand side is all first derivatives, and the right-hand side contains only the dependent variables with no derivatives. Having converted the system of second-order ODEs into a first-order system, we can write a function to implement this system as we did previously. The function falling body 3 has two inputs. The first input is ignored, and the second input vector z can be used to calculate the output vector of derivatives. In this case, there are 4 terms to calculate for the dz vector, but the process is essentially the same as that used previously for a one-dimensional trajectory. In the script cm_Venus spacecraft 4D system.m, we solve the system we just created using ODE 4.5. The initial value is a vector, now a vector of 4 values, x, x dot, y, and y dot. The output z is then a matrix with 4 columns, one for each component. By extracting and plotting the output, we see that the descent initially moves quickly in both the vertical and horizontal directions. After 27 seconds, the velocity in both directions starts to decrease dramatically as the atmospheric density begins to significantly increase. After 40 seconds, the craft drifts slowly down vertically.